Assalamualaikum and a very good day. This is Dr. Hidayat. Today I'm going to share with you the general CFD simulation for dummies. So there are 7 core procedures of CFD simulation process. The first one, create 2D or 3D model. Second one, assign the computational domain. And next, mesh the computational domain. Number 4, assign the boundary condition. Number 5, execute the calculation. Number 6, mesh refinement and validation study. And finally, data presentation. So the first one, create 2D or 3D model. The initial step for CFD simulation process is model creation. Since CFD analysis employ numerical calculation technique that apply at the body of the model, sometimes known as domain. Thus, this process is essential for further analysis. The model creation can be done using any CAD tool such as CATIA, SolidWorks, AutoCAD, and so on. So this is the problem or the model that we need to investigate. So for this case, this is the pipe casing. We have 1 inlet and 2 inlet. Definitely we have 1 outlet. So number 2, assign computational domain. After the model has been created, you must choose which section act as the computational domain. Not all the model can be assigned as the domain. The computational domain is a region for numerical calculation to take place. For example, as you can see here, the casing below shows the pipe model. If your simulation focuses on the fluid region inside the pipe, then you should extract the fluid which is inside the pipe casing as the computational domain and remove the pipe casing as shown in figure 3. So this is the pipe casing and we extract the fluid region and form it as the computational domain. As you notice, I extended the outlet and inlet because for this case, I want to make sure when the flow of fluid inside the entrance, it is fully developed flow. The next one is a mesh the computational domain. The computational domain now can be meshed using any tool like ANSYS mesh mode analysis or others. The reason mesh is needed because CFD calculation carried out using finite volume method FVM. Thus, the small pieces of volume must be generated from the computational domain as shown in figure below. In this figure, polyhedral, as you can see, polyhedral mesh was used to generate the meshes. You can apply any type of mesh such as triangular, rectangular, or any kind of shapes. Number 4, assign the boundary condition. During the meshing phase, you can apply boundary condition to the domain. For this case, you may apply inlet and outlet phase at the right location so that the CFD simulation can be calculated without error. So as you can see, during the meshing phase, you need to assign, for example, this one as the inlet or outlet. And then you can do the CFD setup at the ANSYS Fluent. The next is execute calculation. After the boundary condition has been assigned correctly to the domain, you may proceed with the calculation. This calculation will be done to calculate the governing equation if you involve of 3D, which is governing equation in X, Y, and Z for conservation of mass, momentum, and energy at every cell centroid. This is an example of iteration process against the residual error. The next one, the most essential in any numerical CFD simulation is mesh refinement study and validation. The ideal CFD mesh has an infinite number of cells. And of course, the infinite number of cells cannot be generated and solved in practice. Thus, the finite number of cells has to be used instead. Unfortunately, there is an error associated with the finite number of cells because the solution variable like velocity or temperature in CFD normally varies linearly across the cell. This error is called discretization error. This error, however, can be controlled and minimized by using mesh refinement study or mesh sensitivity study. This process involves a series of meshes with increasing level of refinement are used to solve in CFD problem. Once discretization error has been estimated, the mesh can be chosen that has both an acceptable level of accuracy and a reasonable compute time. As you can see here, this is the example of mesh refinement study for aerofoil. So the point of interest is lift coefficient. The first one, we need to generate three types of meshes: coarse mesh, medium mesh, and fine mesh. So different type of mesh will give different result. For this case, lift coefficient result. So you need to tabulate the result based on different category. So as you can see here, the horizontal axis represent the representative cell length. So what basically is this length? This is the length of a mesh that represent to your computational domain. For example, this one, okay, as you can see, we have so many number of element or cell. So representative cell length will reflect to the one number of size that represent to the whole of the meshes here. So as you can see, the bigger number of cell length represent the coarse, and the small represent the fine mesh. After some mesh has been generated, that begin with coarse, medium, and fine mesh, extrapolated phi or quantity of your interest can be calculated using recursion extrapolated method. So this one you can follow in order to predict, alright? In order to predict the phi value at 0 representative cell length. This method able to predict the phi value based on the projected data from the previous 3 cells, which is coarse, medium, and fine. So recursion extrapolation method can be used to project the phi value based on 0 representative cell length. So how to quantify, how to get the error or to calculate the error? So this is the method. Remember that at the 0 representative cell length, this is the ideal case. So we make it here as a reference, point of reference. So in order to get the extrapolated error, which is the fine mesh value minus with the phi value at the 0 representative cell length over phi value at 0 representative cell length. And finally, you can perform validation study by comparing your CFD result with experimental data for your reference. So this is another point of interest. I want to look at on the drag coefficient. So this is the angle of attack. So the blue represent the experiment and the red represent the CFD simulation approach. And finally, data presentation. There are a variety of methods that can be used to post, process, and present CFD solution data. Contour plot, line, graph, and table are the most popular and are sufficient for the majority of CFD analysis. If the data are not presented clearly, it can be difficult for readers to understand the physical nature of the solution and assess its accuracy. For example, you do the simulation, this is the result of the simulation. The simulation will give in terms of value only. The vector form, U1, U2, U3, the pressure form, the temperature, and so on. So you yourself need to convert into visualization or data presentation. Make sure the reader understand your interpretation. It can be done using the line graph, the contour plot, or the table. This figure, for example, is the contour plot for the pressure in the cross section of the aerofoil. So this is the pressure distribution. As you can see, this is the continuous and discrete band. So from here, the red color represent the positive pressure and the blue color represent negative. And the green color represent the transition from the negative to positive pressure. If you use the discrete band, you can actually analyze where is the location of transition. That is why you can see discrete color band are always preferred. I think that's all about the general CFD process. Thank you for your kind attention.